Yeah, all right. Hi, everyone. My name is Megan Masterson. I'm a graduate student at MIT working with Aaron Kara, as well as two postdocs, Kishale Day and Christos Panagiatou. Christos is here. Kishale is not. And today, I'm really excited to be telling you about a new population of mid-infrared selected TDEs. So I think we've already seen this plot today, which is just showing you the cumulative number of TDEs discovered to date. It's slightly out of date now. But I just want to highlight that we're really entering this kind of era of population studies of TDEs now that we've grown to more than 100 events. And really this has been made possible due to these large time domain optical surveys, which we've heard a lot about today already. But I'm going to argue today in this talk that you really need to take a multi-wavelength approach in order to get a full census of TDEs. And I'm going to kind of motivate that by talking about a few surprises from our initial studies of the TDE populations. So the two surprises that I'm going to focus on today, we've already actually heard about. And they are that TDEs prefer these unusual host galaxies, and that the total energy that you observe from a TDE is roughly 10 times lower than what is expected based on just theory of unbinding a star. So let's talk about the first. So I think you've also seen this plot like 3 times just this afternoon. But this is a tracer of the star formation rate of a galaxy. So on the y-axis here, you have your H-alpha in emission, tracing your active star formation. On the x-axis, you have your H-delta in absorption, tracing your star formation on much longer timescales, these A-type stars. And I've highlighted some important regions on the plot here. So you can see that we have our star-forming galaxies up here with a lot of H-alpha emission, your passive galaxies down here with very little H-alpha emission. And as we've highlighted before, there's this kind of regime over here that only make up like 0.1% of SDSS galaxies. So these are the post-starburst galaxies, which show a lot of H-delta in absorption, but very little H-alpha in emission. So a recent burst of star formation that has since ceased. And these are where the optical and X-ray TDEs lie today. And you can see that a sizable fraction lie down here in this post-starburst regime. A significantly higher percentage than what you typically see in your SDSS galaxies. And so the question is this driven by an actual intrinsic change to these sorts of galaxies that are making TDEs more likely to occur, like mergers, as we've heard about, or is this a result of selection effects? So we'll come back to this, and you'll see why in a bit. And now I want to talk about the total energy output of TDEs. So this has been dubbed the, quote, missing energy problem. And so on the left here, you can see the optical TDEs, their total integrated energy as a function of black hole mass. These are from an earlier paper. And then you can see in orange the kind of 2 extremes of the theory. And you can see that roughly the optical TDEs lie about an order of magnitude lower than what you expect from theory. There have been a number of potential solutions that have been thrown around. The one that I want to focus on today is that most of the energy is radiated away in the extreme ultraviolet, which we don't have access to. But can we actually study this EUV indirectly? I'm going to argue that yes, we can, and that the best way that we have to do this right now is to use dust. So when you have your intrinsic optical UV and X-ray emission, if there's dust around the supermassive black hole, that dust will absorb this light, it will heat up, and it will re-radiate in the infrared thermally. And this really gives you kind of a full census of the total amount of energy that is output from the TDE, because dust is very sensitive to all of this emission, even the EUV that we can't see. And so really the kind of satellite that has been great for studying TDEs in the infrared is WISE. So WISE was launched in 2009, and it completed its primary mission in 2011, scanning the entire sky in 4 different filters. But since 2013, it's been reactivated and is scanning the sky now every 6 months in the 2 shortest filters. And so really I want to highlight that WISE provides an exquisite long baseline for us to study transients, and in particular to study these kind of longer transients like TDEs, which last for longer than 6 months. And so the first kind of attempts to look for this mid-infrared dust echo from TDEs occurred when we looked at optical TDEs in WISE. And there were a number of papers that came out in 2016 which found this emission from numerous of the optical TDEs. And so it's consistent with dust that's at roughly 0.1 parsecs with a covering factor on the order of 1%. And since then, there's been follow-up work that has looked at a larger sample of optically selected TDEs from more recent data and found that this kind of 1% dust covering factor seems to be relatively universal in the sources that have been detected. So that kind of makes sense if you look at this picture that I put up earlier, with the idea being that when you're seeing the optical and UV light, you can't have a ton of dust that is obscuring that emission. However, there also might be TDEs which look more like this, where the dust is covering a much larger fraction of your line of sight and blocking the emission that you can see in the optical and UV. And so our group has been interested in finding these sources and seeing if they can help us solve some of those surprises that I mentioned at the beginning of the talk. We're not the first to have done this, so I want to highlight just one group that has done this before. This is the Morong sample, which stands for the mid-infrared outbursts in nearby galaxies, and I'm showing an example of a few of their sources on the left here. So Morong did a slightly different study than what I'm going to talk about today, where they used integrated photometry from WISE. They restricted to SDSS galaxies within a redshift of 0.35. And importantly, they made no past cuts on AGN activity. And so I think that there are a high number of sources in this sample that actually are AGN, as we've heard today. It's kind of difficult to distinguish sometimes between AGN and TDEs. But I think it's very important to do so if you want to talk about things like rates and host galaxy properties, et cetera. And I should also say people have also done this looking at ultraluminous infrared galaxies as well. But a number of these also show characteristics of AGN activity. So that brings me to our work. So we've been using what we call the WISE transient pipeline, which was developed by Kishley Day at MIT. Kishley is running basically difference imaging on the entire WISE pipeline database. And so basically taking your science image, your reference image, subtracting them, and looking for nuclear variability in galaxies without having this kind of overwhelming amount of stellar light in the way, basically. And so this is actually an example of the first TDE that we found in a paper that was led by Christos. And now I'll just walk you through kind of how we select TDEs, because it's a bit different than in the optical, because things are a little bit more complicated here. So first, we restrict to nuclear sources. For our first volume-limited sample that I'm going to discuss today, we restricted to galaxies within 200 megaparsecs, and these are all spectroscopically confirmed galaxies. And we restricted to things that had a TDE-like light curve, so something that shows a fast rise followed by a monotonic and slow decline. We had to make luminosity cuts to make sure that we are kind of ruling out most supernovae. And we required things to be detected in WISE for at least 5 epochs, which is 2.5 years. That's relatively long for TDEs, but again, this is to make sure that the total integrated energy is something that's reminiscent of an accretion-driven flare rather than something like a supernova. And we cut on WISE colors to make sure that we're ruling out any sort of AGN activity. And so I think one of the most exciting results from this sample is that we actually found the closest TDE discovered to date. So this is that TDE. It's got its WTP name, but it's also in the galaxy NGC 7392. This was a paper led by Christos. And this TDE was completely missed by optical surveys. And it's at a distance of just 42 megaparsecs. And you can see it's got this fast rise up to about 100 millijanskis in WISE, and then followed by this slow decay, just like we had kind of selected for. And on the bottom panel here, you're seeing basically the optical and a few X-ray data points, which show basically no transient coincident with the TDE. So to rule out past AGN activities, we're constructing this sample. We made a number of cuts. The first is that we excluded anything with sort of extraneous variability. So I'm showing one example of something that wouldn't make the cut here because it's just too highly variable before the kind of key flare. We also cut on WISE colors. So these are showing the sources in our sample that basically none of them sit near the boundary for AGN. And finally, we obtained optical spectroscopic follow-up And we've basically ruled out anything that kind of sit in this Seifert land up here. Yeah, and we found very little AGN contamination from this sample. And so the total sample has 12 sources within about 200 megaparsecs. You can see them all here. They all show kind of a very similar light curve shape. That's by selection. And in a sense, that is kind of biasing our dust distributions, but this is kind of the first step that we can take. And the majority of them are completely optically faint. So you can see there's basically no detections in the optical. There are a few that do show optical detections, namely this one down here. It's difficult to see because it's a relatively short-lived optical flare. But yeah, the majority of them do not show optical transients. So now I want to revisit with this sample those surprises that I highlighted at the beginning of the talk. The first being that TDEs prefer these unusual host galaxies. So if we go back to this plot where we found that the majority of optical TDEs are sitting in this post-starburst regime, now if I add the infrared selected TDEs, you can see that actually the majority of infrared TDEs do not lie anywhere near the post-starburst regime. And so what this is pointing to is that we're kind of finding this kind of elusive class of star-forming TDEs, and we're not finding the same sort of selection biases that might be occurring in the optical. This is not to say that optical TDEs aren't occurring in post-starburst galaxies, because they definitely are, but this could be driven in some part due to a selection bias against things in dusty environments. Also, if you just take a look at the host galaxies, they actually look quite different than the optical TDEs that Erica was showing us earlier today. And if we actually compare them, you can see by eye that we're seeing a lot of things that look like they have much more spiral features. We do have a couple of very interesting sources with these kind of merging tails and whatnot, but for the most part, these look much different than these kind of little blobs that you see in the optical regime. Part of this could be driven by the fact that we are working at much closer distances. We're only going out to a redshift of 0.05, whereas most optical TDEs are found beyond that. But I think there is some reality in the fact that we're finding kind of more spiral-looking systems. So in summary, our IR TDEs tend to be found in a more representative sample of galaxies. And actually, statistically speaking, if you looked at that distribution of IR TDEs compared to SDSS, they're completely consistent with being drawn from the same population. So I think this is an exciting step forward in our understanding of kind of where you expect to see TDEs. Now, the second surprise that we talked about at the very beginning was this missing energy problem. So now here is that same plot from earlier, but with our infrared selected TDEs in purple here. And you can see on the right here is just the histogram of those sources as a function of their integrated energy. And you can see that we're getting much closer to the kind of theoretical expectation with these infrared selected TDEs. So this is probably telling us that at least some fraction of the energy is released in the EUV that's not being accounted for in just the optical alone. However, there are some caveats with this. So you see that I plotted all of these with little error bar or upper limits or lower limits here. And that's because there's a significant uncertainty in what we're doing with WISE alone. So WISE provides you with 2 photometric data points. So you can fit a black body, but you can't learn much more about the dust spectral shape. And that's really important when you want to talk about energetics. So for example, we don't know what the dust composition is. We don't really know what its temperature is. We have a good guess, but it is highly dependent on your assumptions that you make. We don't know what the grain size is, et cetera. And so because we don't know those things, this is kind of the best we can do with that integrated energy right now. The other thing that we don't know is the covering factor, because we don't often have any optical emission to compare to. However, we have some lines of evidence that point to a relatively high covering factor in these sources. Namely, we're not seeing our optical and UV emission. But yeah, I think this is an exciting step forward, but there's still some more work to be done with this sample of infrared selected TDEs. Yeah, so in summary, they're closer to theory, suggesting that at least some of the radiation must be emitted in the EUV. The rates are very consistent with what's being found in the optical and the X-rays. So here is our luminosity function on the right here, with the purple showing you the infrared selected TDEs. And I'm comparing to the X-ray luminosity function from the Rosetta team in green and the optical luminosity function from Yuhan's 2023 paper in orange. The luminosities here are not quite exactly the same, so take it with a grain of salt. But the important thing is that the total integrated rates are very similar between all of the selected samples and point to, if we're not seeing these infrared TDEs in the optical or the X-rays, the total rate is slightly higher than all of these three individual rates alone. One of the kind of surprises that came out from this sample is that there's actually transient X-ray emission in 3 out of 7 of the sources that are in the German half of the Rosetta sky. And they have a variety of spectral shapes, just like we have seen in the X-rays, from optically selected and X-ray selected TDEs. So we have one source that shows a relatively hard X-ray spectrum, akin to something that you would see when you are heavily obscured by dust. But we actually have 2 sources which show relatively soft X-ray spectra. The one thing that I should note is that all of the X-ray emission is quite dim. So you really need to go with kind of a deep stare to be able to see these TDEs. So what's next? There are a number of things that we're still working on, and I think this is an exciting time to be studying TDEs in the infrared. We're working on homogenizing the X-ray sample, so we're working with XMM to go down to the same flux limit as Rosetta. We also have approved cycle 2 JWST observations, which will provide the first view of TDEs in the mid-infrared with JWST. And this is going to be very crucial for probing the total energetics of these sources, because this will allow us to get a handle on the dust content, the grain size, et cetera, all of those things that I mentioned that affect our ability to do energetics. And it'll also allow us to search for high ionization emission lines and other exciting things. We're also working on doing radio follow-up with the VLA, and we're doing more work on host galaxies, looking at central concentration, et cetera. And then I think, importantly, we need to go to larger distances in order to be able to see these kind of rare events that will show us kind of that turnover at high luminosities, at high black hole masses. So we're working on a flux-limited sample as well. So my takeaway from this is just that there is a lot left to do, and it's kind of an exciting time to be working on infrared TDEs. So with that, I'll just say that the kind of key takeaways that I want you to walk away with are that you really need multi-wavelength discovery methods to obtain the full census of TDEs, and that IR-TDEs help solve this problem of host galaxy demographics as well as the missing energy problem, and they're occurring at a rate that's comparable to your optical and X-ray selected populations. And if you're interested, the papers are linked here. Thank you.
Okay, questions? Go ahead, start there.
Yeah, great talk, thank you. So I kind of have 2 maybe related questions. One is, when you're comparing the sample of SDSS, right, these mid-infrared galaxies necessarily require dust, right? So
Yeah.
Besides your selection bias of choosing pretty close galaxies, are you also selecting on like very dusty galaxies, and that's why you have a little
That is a great question. So that's initially kind of why we targeted this sample, was we were looking for kind of dusty galaxies that seem to be missing in optically selected samples. I would say we still have more work to do on that front. We definitely need to have dust near the nucleus. Whether or not dust near the nucleus correlates with dust in the host galaxy, I think is something that is highly uncertain, and yeah, people argue both ways. So we're working on that. That's another thing that is on the list of things to continue working on. It's a great question.
And then related to that is the idea that wouldn't a collection of optically selected TDEs be almost mutually exclusive with infrared TDEs? Because if there's dust, it's going to be blocking the optical, and the optical is going to translate into infrared.
Yeah, I mean, it's a question of viewing angle and the dust geometry, right? If you have a spherical shell of dust that surrounds your entire black hole, sure. But if it's more like toroidal, then you can imagine a viewing angle where you're only seeing the kind of edge-on systems, just like in AGN or something like that. So, yeah.
Somewhat related question. Can you comment on any potential connections with the extreme coronal line emitters or ambiguous nuclear transits, many of which also show very similar looking infrared flares?
Yeah, that is a great question. So I will say that we have, so all of these sources were detected more than 5 years ago. Our turn-on time is 2014 to 2018. We have one source that turned on in 2018 that shows the formation of coronal lines in 2023. So yeah, I think that one source is a nice kind of connection between what TDEs look like in gas and dust-rich environments. I think we're going to keep following these up and see if we see the formation of coronal lines in any of the other sources. But yeah, I think it's a good point.
So obviously we've done optical, these specific ones on optical light hair, but there's been ones like yours, papers that do have optical and IR emission. Have you compared just like with the population of optical light hairs in their time scales and thought about like what that would mean for the amount of dust and the geometry of the dust that's being processing the emission in these cases? Because I can't remember exactly, I couldn't quite see from the plots, but they're much longer, but much slower evolving. And in principle, if you assume some sort of like weeks, month flare, then was, producing it, that would be interesting.
Yeah, so I can show you we have modeled, went too far. So we've modeled all of the infrared light curves with a spherical shell of dust. This, intrinsically, you have to assume something about the input light curve. So it doesn't really change things that much, but what we've assumed is an input light curve that goes like t to the minus 5/3. From this, we can back out some of the parameters that are similar to what people model in the optical. I remember doing this at the beginning, trying to compare things, but I think there's a large amount of uncertainty on it that doesn't allow you to do quite that comparison. The one thing I will say is that you do expect the kind of optical light curves to be smeared by this reprocessing, so it's not surprising that they're longer lived.
No, that's totally what I would expect, but no, I didn't remember that even,
Yeah.
that you have estimates of like dust location. Those are kind of
Yeah, it's like 0.2 parsecs or something like that on average.
Thanks for the great talk. I was just going to comment that I think we already were seeing in these, years to decades long UV light curves that there's a lot of energy coming out at late times.
Yeah.
And I don't know if your echo models will really be able to distinguish whether this energy was coming out in months or if it's actually coming out over in this sort of plateau phase over several years. I mean, you can put an upper limit. I mean, it couldn't come out over obviously longer than the duration.
Yeah. I think the majority is coming out near peak, but they are long-lived, so there is some level of emission, but these are on log scale, these plots, so yeah, so I think most of the emission is coming out near the peak of the event, but yeah.
My question was with regards to your optical upper limits. Of course, we do have some, the Rosetta X-ray TDEs that don't produce detectable optical. So are we really sure, especially these cases where you see soft X's, are we really sure that the line of sight is obscured for those, or could they be consistent with the type of TDEs we see?
Yeah, I mean, they definitely could be. I think they're a little bit dimmer, if I'm remembering correctly, in the X-rays than the Rosetta ones. But one of our TDEs was actually detected as a nuclear transient in Rosetta as well. So we sent them our coordinates, and they were like, "Oh, we're actually already looking at this one." So it's definitely possible that what we're seeing is kind of the X-ray ones that.
It could be these are 10% covered in dust versus 1%.
Yeah, I mean, it's very difficult to determine what the covering factor actually is. Yeah.
That's great, thank you. I may have missed this. Is there any overlap between the optical samples at this time and the infrared? In the sense, do you recover infrared emission associated with any known optically selected TDE?
We do not. We detect one source which is classified as a changing look liner, but that is which looks kind of like a TDE, except it occurred in a galaxy. And actually, there's been a paper recently that claims that it's a TDE based on the infrared. I think that the primary reason for that is that we are looking much closer. So our sample only contains a handful of optical TDEs. I know there are some close optical TDEs that also have strong dust echoes like 2019 QIZ. But the thing is that our turn-on times are 2014 to 2018, so we're limited in terms of what optical TDEs we're looking at.
One random question. Your selection criteria included the selection on light curve shape.
Yeah.
So is the implication that there are transients that satisfy all of your other conditions but don't have that shape?
Yes, the light curve shape was mostly chosen so that we ruled out things that looked like AGN. I will say this first sample contained about 2,000 transients in the nuclei of galaxies. And so we did a lot of this by eye, but in our flux limited sample, we're going to try to be a little bit more agnostic to kind of the light curve shape. The light curve shape is set entirely by the dust distribution. So in a sense, this fast rise followed by slow decay means we're selecting something with kind of a spherical like shell of dust. Yeah. Mm-hmm.
When you look at those, do you use dust lanes, or when you look at like smaller planets, do you see evidence that those are dust?
That is a great question, and not something we haven't looked into yet. Yeah, I have an undergrad student who's going to look into the Balmer decrements, but we haven't done it yet. Yeah.
Yeah, we should chat. I'm super curious.
Yeah.
I would definitely predict that. Like, if you had asked me before, I would have said that you'd be finding a bunch of like starburst galaxies very highly starred.
Yeah. Yeah, it is puzzling, and also I'll say that a lot of these systems are pretty red, which was surprising to me at first. So I thought we were looking for like the blue kind of typical spiral galaxies, but I think a lot of them are going to be heavily dusty in the entire galaxy as a whole. Yeah.
Short follow-up. When you compare these to the neurons, you've got additional AGN selection. Are these a subset of the neurons, or are there more of these that were not?
Yeah, so there are more, and that's because we do all sky, and they restricted to SDSS. So I think of our 18 sources, we cut out 6 in terms of AGN cut downs. Of our 18 sources, I think 6 are in the Morong sample, if I'm remembering correctly. But yeah, we have a bunch of southern sources. So for example, 7392, the closest TDE, I think the reason that has gone undiscovered was because it was in the south and not covered by SDSS.
Really interesting. One question I had was, because these sources are closer, you're using SDSS spectra, I believe, to place them on the H alpha, H delta diagram.
Some of them, yeah.
Okay. So there is an issue of aperture bias where you've just been staring at the center of the galaxy with the spectra.
Yeah.
And that is a distinction with the work done at higher redshift, where more of the galaxy is included in the fiber. So have you looked into that at all with your long slit data to see whether there are any biases inherent in how you're typing the galaxies with their spectra?
Yeah, it's a good question. We didn't look into it with the SDSS galaxies. We do have a bunch of long slit spectra from Magellan, most of which don't cover H delta, sadly. So we only have a few sources where we got Gemini or SOAR. But yeah, we haven't actually looked at that, so that is a good idea to cover. Yeah.
So for the sources that have unobscured X-rays, what is the relative phase of the X-rays to the infrared? And do you also have optical limits? So because you say unobserved X-rays, right, and infrared, so where is the optical?
It's a great question. Yeah, so we only have X-rays from later on. So I think 3 years post-detection. One source is detected in XMM SLU, and then detected in Rosetta at 10 times lower flux. So it shows kind of a similar long-lived decay. But the other source that looks unobscured, we don't have any constraints from around the time of peak. Yeah, our limits primarily come from Assassin, but we've also checked Atlas to go a bit deeper. Yeah.
Okay, if there are no more questions, let's thank Megan again.